Hello, Math 8 students. This is Open Up Resources, Unit 2, Lesson 1, Projecting and Scaling. We are going to start off with this number talk as a warm-up. It asks us to find each quotient and write our answer as a fraction, an improper fraction, or a mixed number. I want you to get started just by answering 6 1/4 divided by 2. I want you to see what you can recall and do on your own before you continue in the video. Hopefully you've given it a try. Let's take a look. 6 1/4 divided by 2. I first want this to be an improper fraction. We can't really calculate very well with mixed numbers, so we're going to change it to an improper fraction first. And 6 1/4 is the same as 25 fourths. I have 6 wholes, each cut into 4 pieces, gives me 24 pieces, plus one more piece is 25 fourth pieces. We're dividing by 2, and we remember from last year that dividing by 2 is the same as multiplying by the reciprocal 1/2. So 25 fourths multiplied by 1/2. And when I multiply fractions, I simply multiply straight across. So 25 times 1 is 25, and 4 times 2 is 8. So 6 1/4 divided by 2 is 25 eighths. I wrote it as a fraction, an improper fraction. Another strategy that works really well for some of these problems is just thinking of it conceptually, dividing it by pieces. So we have 6 1/4 divided by 2. To work through this problem, think of it as 6 1/4 pies that's left over after Thanksgiving dinner. And you're going to send some over to your neighbor's house, and you're going to keep the others. So what are you going to do with those 6 pies? Well, those 6 pies need to be split among the 2 households. So 6 split among the 2 households is equal to 3 whole pies for each household. But that's not all. We also have that 1/4 of a pie, and we want to keep things fair and equal. So I'm even going to take that 1/4 of a pie and split it among the 2 households. 1/4 divided by 2, that means each of us are going to get 1/8 of a pie. So altogether, the 6 divided by 2 is 3. The 1/8, or 1/4 divided by 2 is 1/8. And so putting it all together, I have 3 plus 1/8, which is equal to the 3 1/8. This is our mixed number, this is our improper fraction, and 25 eighths is the same as 3 1/8. Hopefully that was a good reminder, able to boost your skills a little bit. I want you to continue on now with the 10 1/7 divided by 5. Try and do it using our 2 different strategies that we discussed up above. Turn it to an improper fraction and do that division using the algorithm, but then see if we can also do this one mentally, similar to what we did here in red. All right, let's take a look. 10 1/7 divided by 5. This time, 10 1/7, so again, this is 10 wholes, each cut into 7 pieces. So that's going to be 70 pieces, plus one more. That gives me 71 sevenths. And dividing by 5 is the same as multiplying by the reciprocal 1/5. So 71 sevenths multiplied by 1/5. And now it's a multiplication problem, so we multiply straight across. 71 times 1 is 71. 7 times 5 is 35. And we are done. But now let's think about this in a similar way to what we did up here. I have 10 whole pies that I'm going to split among 5 households this time. So 10 divided by 5 is 2 wholes. But now we need to take this 1/7 and we also need to split it into 5 pieces. And again, we can think of this in a very conceptual way. I'm going to attempt to draw a pie that is cut into 7 pieces, and I only have 1/7 of that. Now this is not going to be perfect, so I hope that you'll be patient with me as I work through this. All right, that's my attempt at 7 equal slices. It's not perfect, but I hope that it's close enough. And I have just 1/7 of those. So all the rest of these pieces are already gone. But again, I want to be fair, and I want to take this 1/7 of a piece and I want to split it evenly among those 5 households. So that means this is going to have to be split into 5 pieces. Let's see if I can find a good color for that. 1, 2, 3, 4, 5. So they're each going to get just this tiniest little sliver. But how much is that with respect to the whole? In order to really see how much it is with respect to the entire whole, I'd have to imagine that this piece here is also cut into 5 slices. This piece was cut into 5, this was cut into 5, this was cut into 5, and so on. And so if that whole entire pie was cut like this, that would be 5, 10, 15, 20, 25, 30, 35 total slices, and we're looking at just one of those slices. So that 1/7 divided by 5, that's how I get 1/35. If that doesn't help, you could also have thought of it as dividing by 5 is the same as multiplying by the reciprocal, and I get 1 times 1 is 1, 7 times 5 is 35. Either way, we get the same answer. And now I have 2 whole pies and 1/35. That's the mixed number, same here as the 71/35. We can complete this problem in a similar way. Not quite as straightforward, not quite as simple, but it can be done. For the sake of time, to cut this video a little bit short, I am going to move on, and we'll save that for another time. We are now to the sorting rectangles. Prior to starting this video, you should have watched the first video where I taught you how to cut your papers into these rectangles, and so we're going to be looking at those rectangles now. These rectangles, as you remember, were made by cutting that 8.5 inch by 11 inch paper in half again, and half again, and half again, and you can see it here in the diagram. This diagram matches the same way that it was when we laid all of those pieces back out to form that whole paper. So what we're going to do now, before we actually complete the activity with the rectangles, I want us to take a minute and find the dimensions of each rectangle. Now you can do that without actually getting out a ruler and measuring. In fact, if you get out a ruler and measure, you're probably going to do it imperfectly. It's better if we just calculate what these dimensions are. For example, I know that rectangle A is 8.5 inches by 11 inches because that's the whole sheet of paper. Rectangle B, what are the dimensions? Well, we can see that this is the length. That would be 8.5 inches. That was easy enough. This is the height. How am I going to figure that out without getting out a ruler and measuring? Remember how we cut that rectangle to begin with. This whole side length is 11 inches, but I folded the paper in half, so this dimension here, this measurement, is half of that 11 inches. So 11 inches divided by 2 is equal to 5.5 inches. Using and repeating that process, find the dimensions of each one of these rectangles. You can go ahead and pause the video, give yourself a chance to think about that, and just write them down just as I am doing here. All right, let's take a look and see how you did. Rectangle C, remember that we split this in half. So this was 5.5, which means automatically this side length here is 5.5 as well. What about this side? Again, think about what we did. This whole entire side length is 8.5, but I folded that in half to get this amount. Half of 8.5, and again, think about how this relates to that warm-up. Half of 8 is 4, and half of half is 1/4. So I don't even really need to use my calculator for these. We're just using that mental math strategy practiced in the warm-up. Knowing that this is 4 1/4, I of course know that the other half is going to be the same dimension, 4 1/4. Now that leaves us with the length, or the height, of this rectangle. Again, refer back to the fact that this rectangle is 5.5, and we're taking half of that. This one's a little bit trickier. Half of 5 is 2.5, and half of a half is 1/4. Let me rewrite that differently. 2.5. And half of this half is 1/4. So if I have 2.5 and another 1/4, that gives me 2 3/4. Knowing that that's 2 3/4, I also know that the other half is going to be the same, and that will also be 2 3/4. And now I'm left with just figuring out half of 4 1/4. Half of 4 is 2, and half of 1/4 is 1/8. I've now written out those dimensions for each one of these, and that's going to be helpful for our next activity. Now we're finally ready to sort our rectangles. Our goal, what we're doing, is we are trying to figure out which copies of, or which rectangles are scaled copies of our whole sheet of paper. There is a little trick that we use to figuring that out. Instead of having to do it all mathematically, we're going to use that little trick, and it's called the eye test. It's going to look kind of silly, but pay attention to the little corner where you can see me. This is how I'm going to do it. I'm going to focus on rectangle E and D first. And what I do is I line them up in front of my face like this. Of course, E is smaller, so I'm going to have E in the front so I can still see it, and behind it is D. And since it's bigger, I can see it just fine. And what we're going to be doing is we're going to be changing the perspective by moving them closer apart, closer to our face, further apart, apart from each other, etc. And as I do this, the trick is I want to close one eye and then change that perspective to see if I can get them to line up. So it looks a little bit silly, but I promise it works. It's pretty cool. So lining these up, closing one eye, and I can see that at this point, I can see that the widths match up, but I can see that rectangle D is still taller. So it's not a scaled copy because they don't line up. I want to see if I can do this in the webcam. Now the reason why we have to close one eye is so that we're only using one lens to see through. And since this camera is just one lens, hopefully we can get that same perspective here in the camera. So again, I'm kind of lining these up so I can see E in the front and D in the back. And if I position them correctly and spread them apart just a little bit, you can see that now it looks like I've got the bottom widths to measure to line up, but I can still see that D ends up being a little bit taller. So I would just be changing that perspective, bringing them closer and further apart, and that's essentially what you're going to be doing with your eyeballs. So you're going to pause the video long enough. I want you to compare all of these rectangles and find out which ones are scaled copies of each other. Specifically, which ones are scaled copies of our rectangle A. That's our full-size sheet of paper. So you'll take A and E. Those have to be really far apart to try and close that eye and get that perspective. What about A and D? What about A and C? And you're going to repeat with each one of these rectangles, trying to figure out which ones are scaled copies of A. Again, you know it's a scaled copy of A if you can do that perspective trick and make them line up perfectly, both with the widths and the heights. So pause the video, figure out which ones are scaled copies. Let's take a look and see how you did. Rectangle A, the ones that lined up perfectly using that eyeball trick were rectangle C and rectangles E. The ones that did not line up with A, but did line up with each other, are B and D. Take a second and let's get those dimensions up here. C, the length of the shortest side was 4 1/4, and the length of the longest side was 5 1/2. Now, because I know that I'm going to be calculating with these numbers, I'm also going to do the decimal approximations because they're easier to calculate with. Continue on filling out your table with all of those dimensions. Continue when you're ready to go. Check to make sure that your tables match mine. Make sure that we're always comparing the short side on the left and the long side on the right. Now, look at the measurements in the look at the measurements of the rectangles of the scaled copy of A. We want to look for any sort of relationships we see among those numbers. So I'll give you a hint. How does a 4 1/4 change to be an 8 1/2? Hopefully you can see that that measurement, 4 1/4, doubled is 8 1/2. And that should make sense. Think about how we created that rectangle. Rectangle C is half of that length. So we multiplied by 1/2. Interestingly enough, we're going to be seeing a very similar relationship over here. 5 1/2 doubled is 11. And again, that makes sense because this length is half of that piece of paper. Those are the kinds of relationships that I'm wanting you to figure out. How is this 2 3/4 related to the 5 1/2? Is it the same relationship as what we see over here? How is this 4 1/4 related to the 2 1/8? And are we going to be seeing the same relationship over here? Take a second to enter these things into your calculator and come up with your own conclusions. And I hope that you see now that 2 3/4 doubled is 5.5. And we do see that same relationship over here. 2 1/8 doubled is 4 1/4. 4 1/4 halved is 2.125. And notice how I wrote that. I did say halved. That's the same as dividing by 2, but I wrote it as multiplying by 1/2. It's because I'm trying to make some connections here. This would be our scale factor. Since these are scaled copies, we're looking at how it's changing. We're multiplying by 1/2, so of course this would also be multiplied by 1/2. And we can also make that connection here. How does the 2 3/4 change to 11? We can do this in 2 steps. We double and double again, which means we are multiplying by 4. Which means, going in that reverse order, we would see that the 8 1/2 multiplied by 1/4 gives us the 2 1/8. We've got this whole table loaded up with all sorts of relationships. Now, I want you to do the same thing here. We have B and D. These ones are not scaled copies of A, but if you did that eyeball test, you notice that B and D are scaled copies of one another. So look for those similar relationships here with B and D. And again, we can see that 4 1/4 doubled is 2. Let me say that again. 4 1/4 doubled is 8.5, and 2 3/4 doubled is 5.5. Which means that if I'm going in that reverse order, I'm going to be seeing that if we multiply by 1/2, we're going to be scaling it down. Now, what if I look for relationships that will take me from this first spot in the table down to this table? Is there a way that I can change this 8 1/8 to 5.5? Now that's not quite as obvious. We're not seeing a connection quite as easily. But as I've mentioned in the past, if you don't know how to go forwards, work backwards. What that means is I don't know how to take 8.5, multiply it by a number, and get 5.5. So instead of trying to multiply and go forwards, I'm going to work backwards and divide. So what I would be typing into the calculator would be 5.5 divided by 8.5. Let me fix that because we can't use those mixed numbers when we're trying to calculate. So 5.5 meaning 5.5 divided by 8.5 meaning 8.5. And when we type that into the calculator, we get 0.64705. There we go. So what that tells us is I didn't know how to go forwards, so I worked backwards. And in working backwards with that division, that tells me that I can now take that 8.5, multiply it by that 0.64705. And yes, there are extra decimals, extra digits there in that decimal, but this is going to get us close enough. You can check and see that you'll get very close taking that 8.5, multiplying it by 0.64705. It's going to get you really, really close to that 5.5. We're going to be a little bit off because I didn't use all of the available decimals. So let's see, can I multiply that 11 by the same number and see if it works? We're going to try it. 11, if I multiply it by 0.64705, it should get me really, really, really close to that 8.52. So 11 times 0.64705, and I actually only ended up at 7.11. That's not very close at all to the 8.5 that it was supposed to be. So that further confirms that these are not scaled copies. We already knew they weren't because they didn't match that eyeball test, and now this further proves that they are not scaled copies. So hopefully that answered that question of things that we noticed about those relationships and those measurements. And now what I want you to do, I want you to make 2 stacks. We have A, C, and E that were scaled copies, and we have B and D that were scaled copies. Make your 2 stacks just like this, where we're stacking all of those bottom corner pieces all together. Now, using a very long straight edge, meaning a very long ruler, a yardstick, a measuring tape of some sort, I want you to see what happens when we draw a line from the bottom corner to the top right corner. I want you to notice that in doing that, we went through the diagonal and hit that vertex of rectangle E. We went through the diagonal and hit that vertex for C, and we continued through the diagonal and hit that vertex for rectangle A. We also see the same thing here with rectangle B and D. When I take that straight edge from the bottom left corner and go to the top right corner, I'm going to notice that again I'm going through the diagonal of D, hitting that vertex, and continuing through the diagonal of B and hitting that vertex as well. What happens now when we stack all of those rectangles from the smallest to the largest? Will we still see all of those vertices lining up? I can try, but I can see I'm going from that vertex to this vertex. That looks very nice. And all the way up to here, that looks very nice. However, you can see that it didn't hit those blue vertices of B and D. I can do the same thing. Here's D, continuing on to B, and you're noticing that it's not hitting the vertices, the vertices of rectangles E and C and even A. So what we can tell from this is that the ones that are scaled copies are all going to line up. All of those vertices are going to line up. And the ones that are not scaled copies are not going to have vertices that line up. Let's write that down. Those scaled copies share a diagonal. It's going to be an interesting property that is going to help define some of these characteristics in this next unit. Are you ready for more? This was something that was very interesting to me. It says in many countries, the standard paper size is not 8.5 inches by 11 inches. We call that a letter size. Instead, in those other countries, it's 210 millimeters by 297 millimeters. They call that a size A4 paper. So now the question is our paper a scaled copy of their paper? Here's the best way to answer this question, because we're dealing with inches and we're dealing with millimeters, and those are different units of measure. So we can't just compare those directly. Here is what I suggest instead. We're going to return to this table where we have our 8.5 inches by 11 inches. We didn't look at this relationship before, but it is going to be a really important relationship to help us answer those questions. Instead of looking at how we can go down the table or how we can go up the table, look at how we can go across the table. Do you know how an 8.5 changes to 11? Through multiplication? Me either. And since we don't know how to go forwards, we're going to use that old strategy. We're going to work backwards and divide. So 11 divided by 8.5. Plug that into your calculator. And yes, you do get a very big, long, ugly decimal. That would be 1.294. And yes, there's many more decimal places, but let's just stop there. I want you to see that that same relationship happens everywhere else in the table. So let's compare this 2 1/8 or 2.125 and 2 3/4 or 2.75. Again, we don't know how to go forward, so let's work backwards here as well. And we would be typing in to the calculator 2.75 divided by 2.125. When we type this into the calculator, I hope you see it. How about that? We're getting the exact same big, long, ugly decimal. Again, that means that when I go forward, I'm going to be multiplying by the 1.294. I did put that in the wrong spot though. It's equal to 1.294 ... So when I go forward, that means I'm multiplying by that 1.294 ... So again, going forward here, I'm multiplying by 1.294. Do it one more time here. 5.5 and 4 1/4. I don't know how the 4 1/4 changes to 5.5 going forwards with multiplication, so I work backwards, and I'm typing in that 5.5 divided by 4.25. Lo and behold, we get that same big, long, ugly decimal. So there is a relationship as we go forward across the table. And that relationship is consistent because it's a scaled copy, and so that's an equivalent ratio. So when we take that information into consideration here, I know that there is a relationship that 8.5 multiplied by that big long ugly decimal of 1.294117647 is going to give me the number 11. So I'm hoping that I can take that 210, multiply it by the same 1.294117647, and get 297. Let's test it out. 210 times that number, is it equal to 297? Putting a question mark because I don't know yet. Typing it into my calculator now though. And we can see that we only get 271. So we are not getting that same relationship that we saw before. If we want to calculate and figure out exactly what number that would be, again, I don't know how to go forwards, so I would work backwards. 297 divided by 210 is a big long ugly decimal of its own, but it is not the same big long ugly decimal that we saw in our other relationships. So that's interesting to note that although we have these different sizes of standard paper, they're not scaled copies of each other. That had me really interested. So what we're talking about so far is it's a new kind of transformation. Last unit was all about rigid transformations and congruence, specifically rotations, reflections, and translations. This that we're going to be talking about in this unit is a new kind of transformation. It's called a dilation. There's a few things that you need to know about dilations. Dilations make scaled copies. That's why we reviewed scaled copies and have been looking at scaled copies, because dilations make scaled copies. Dilations have a center of dilation, very similar to rotations, where rotations had a center of rotation. We would have a point and we would spin around the point. Dilations have a center of dilation. It behaves a little bit different though. And we also need a scale factor. Makes sense since they make scale copies. We need a scale factor to make those scaled copies. So let's focus on this piece. It has a center of dilation. I want to return to our diagrams here. Since these are scaled copies, that means this is a dilation. A dilation is occurring. And the center of dilation is this point right here. Similar, these were scaled copies, so this is also a dilation. The center of this dilation is that point right there. So I want you to think, what does that center of dilation do? What does a dilation do? Before we answer that question, let's practice just a little bit more. 1.3 scaled rectangles. Here's a picture of rectangle R. Rectangle R has been evenly divided into smaller rectangles, and two of these smaller rectangles are labeled B and C below. What I want you to do is I want you to determine, is B a scaled copy of R? Remember, rectangle R is that whole rectangle, very much like our own set of paper rectangles. These ones are just split a little bit differently. Key thing to note though is that they are evenly divided, so they're split evenly. So is B a scaled copy of rectangle R? If so, what is the scale factor? The answer is yes, it is a scaled copy, and the scale factor is 1/2. Think about why. Since it's split evenly, and I can see this very nicely here, B is the same thing over here. So I took all of rectangle R, I basically folded it in half, kind of like we did with our paper, and now I know that this and this are the same. So this is half of R. But we did the same thing this way as well, where I took the height of rectangle R and I folded it hot dog style, cut it in half, so I can see that B is the same as B. So again, I split both the height and the width in half, so the scale factor is 1/2. Now let's look at C and B. Are C and B scaled copies? If so, what's the scale factor? I want you to pay attention to this. Notice I can kind of line these up, right? So it's like taking that rectangle B and I'm splitting rectangle B into 1, 2, 3 pieces going lengthwise, and I'm splitting it into 1, to 3 pieces going with the height. So I split each rectangle into thirds, therefore the scale factor is 1/3. So now think about this. If B is a scaled copy of R and C is a scaled copy of B, is C a scaled copy of R? If so, what is the scale factor? The answer, once again, is yes. They are scaled copies. And here's how we can see this. It's like splitting rectangle R into all of these pieces. So rectangle R would be split 1, 2, 3, 4, 5, 6 ways going along the height, and it would be split 1, 2, 3, 4, 5, 6 ways going the width. So that means I'm multiplying both the height and the width by the same number. That number is 1/6. Let's summarize. Scaled copies of rectangles have an interesting property. It's demonstrated here. Can you see what that property is? Here, the larger rectangle is a scaled copy of the smaller one, and it even tells us that it's a scale factor of 3/2. Notice how the diagonal of the large rectangle contains the diagonal of the smaller rectangle. Here's the diagonal of the large rectangle, and in tracing that out, I also traced out the rectangle of the diagonal of the smaller rectangle. This is the case for any 2 scaled copies of a rectangle as long as we line them up as shown. Here's that hint. This would be the center of dilation. If, however, 2 rectangles are not scaled copies of one another, then the diagonals are not going to match up. We saw that when we tried lining up rectangles A, C, and E with B and D. Those diagonals didn't line up. Now, what is a dilation? This is your cool down. It says, in your own words, explain what a dilation is. I already put what a dilation is earlier in the lesson and earlier in the video, so I will not be answering that question here, which means when you type this into your cool down on Canvas, you're not going to have the official correct answer because I want to know in your words, what is a dilation? Don't forget to complete that cool down in Canvas and your practice problems. That's it for today. We'll see you next time.